let me turn my attention just for a moment to introduce Jim Porter. He's president and founder of Disk Trend. Okay, it's the publisher of the market studies about worldwide disk drive and data storage industries. He first became involved with data storage products back in 1968 when he first joined industry pioneer Memorex. And, of course, he gained all kinds of experience with early handheld calculators at Rockwell, the first consumer video tape recorder at Cartridge Television, and the original computer-controlled video editing system at CMX Systems. And then from there on, in 1974, he began his own management and consulting business. In 1977, he founded Disk Trend, is probably an icon of the industry, and is now consulting with the management of data storage manufacturers. Jim is also founder and active participant of the International Disk Drive Equipment and Materials Association, the Disk Drive Industries Trade Association. So with that, let me turn it over, because we have a great evening tonight, to Jim Porter.
Thank you, John. Yeah, I'm not sure how many people, I know there's one or two in the room who could say the same thing, but the first disk drive I ever saw was the first disk drive. I actually do know there are a few other people in the room that can say the same thing. They were at IBM. I was not. I happened to go to work with a company that received that first disk drive that IBM shipped. About a year after they shipped it, and I used to show it off to business guests with the 24-inch discs and the head assembly moving back and forth and all of that. I used to show it off to probably a couple of dozen people at least over a several-year period. And as I've told many people, the thing that amazes me about that first disk drive is that every time I took somebody down to the computer room to show it off, it was actually working. If you can imagine what the mean time between failure must have been with all those vacuum tubes and all those little goodies. But we're here tonight to talk about how storage has evolved into what it is today, which is a mixture of all kinds of things going on. We're talking here about storage systems primarily. We're not going to spend really any time talking about the storage you use on an individual PC or the storage you use in your cell phone camera, or the storage you may use on any of the other walk-around gadgets which you may have at the moment. We're here really to talk about the storage systems which are used with computers which got a little bit more class than the ones I just mentioned. Now, we could go back, of course, and to early tape drives, and even before that, tabulating cards, and then the early drum memories. But this industry really got started in the way we're thinking about it today with the development of that first disk drive by IBM, which shipped in 1956 with only 5 megabytes capacity, but it had direct access rather than the other types which were available, and it started to be more cost effective. But the big time really came in the middle of the 60s when mainframe computers replaced the earlier attempts to really have high-end computing. And those mainframe computers, those of you who know visible storage below, that IBM 360 came out in 65, and from then on we all talked about IBM and the Seven Dwarfs, if you remember that period, those of you who are old enough, because GE dropped out of the business, RCA dropped out, IBM became the dominant one, and the disk drives and the storage systems which were used became the dominant thing at the time. And the key thing here is we talk about how that evolved. Remember that IBM and a few of the other companies, the Univacs, et cetera, that really were offering computer systems in that era defined exactly what disk drive would be used, and they sold the disk drives basically that would be used for those systems. But then in the second half of the 60s, along came a wave of the plug-compatible drive makers. John mentioned that I had gone to work for the old Memorex in 68. Well, in 68, Memorex became the first of the plug-compatible drive manufacturers, followed not long afterward by Control Data, Century, ISS. The fellows at IBM, when they left IBM, they were called the 12, were called the Dirty Dozen when they left IBM to start ISS, and Marshall and Potter and so forth and so on. Out of that wave of companies came much of this independent storage and disk drive industry which followed. But then along came some other things. Mini-computers. Computers not all had to be giants, they could be mini-computers. And we had, if those of you who knew the Boston area, between 128 and 495, how many mini-computer manufacturers were in that space? A couple of dozen, I suppose. And the small disk drives, out of the disk drive technology which IBM introduced with the System 360, et cetera, and just before it, came the single disk cartridge drive 14-inch in 1965. Shortly thereafter, there were companies like Diablo and Digital Equipment and others that were shipping single disk cartridge drives, which were used then on many, many mini computers around the place. And again, another kind of storage systems. Then again, what happened afterward? Well, at the end of the 70s and the early 80s, this thing called the desktop computer. I don't think we were using the words personal computer right away. That came along a little later as a title. But the desktop computer came along. And partly as a result of that incredible growth in the 80s that occurred and so forth, networks of all kinds really prospered during that period because of those computers everywhere, between the mainframes, the mini-computers, the personal computers, et cetera, and network computing and the storage systems which had to go along to support all of that became an important part of it. So we're going to talk about the evolution from the days when IBM and similar companies defined everything about the storage which went along with their system to the wild scene which has occurred since, the many companies that have come along, and how that's evolved into many, many independent companies offering a variety of different kinds of disk and other types of storage subsystems, the logic, the software to somehow make all that work together, and the evolution of the tape drives that went along with this for archival storage. It's been a wild change of pace, very rapid evolution, and so we've asked the people who are in the session here with us today to talk about what happened, why it happened, how it happened. And many of them were parts of the causes of all of those things. Most immediately to my left is Mike Gluck. Now, I first knew Mike, I'm not sure how long ago, Mike, it was a long time ago, when he was with a company called Control Data, and he was handling the sales and marketing for the storage systems they were selling out into that mainframe universe. But he, after Control Data, was with Fujitsu Computer Products of America, who became a very significant storage system maker, Vanguard Technology, Chaparral, Network Storage, Infusion, and he currently is Executive Vice President Sales of Xiatech, another significant player in the area. Talk about somebody who can talk about a lot of evolution in the industry. Mike is a perfect example. Next to him is Claude Barrera, who is Director of Storage Systems Strategy, IBM Systems and Technology Group. He was a pioneer in establishing computer storage industry standards with the Storage Networking Industry Association, one of the key groups that's tried to make a pattern of something logical out of all those people thrashing around in different directions. And Claude has been a significant leader in doing all of that, and he's a significant leader today in defining IBM's strategy in what they do now. Next to him is another gentleman I've known for quite a few years, Larry Boucher. Larry, I guess, is popularly known as the father of SCSI. After many years with IBM, he left to go to a company called Shugart Associates. And while he was there, he was the key guy in developing Shugart Associates Standard Interface, or SASE as it was called, an intelligent interface which was designed to do something a little bit smarter than what was being done on PCs at the time. And, of course, the industry standards committees didn't allow a standard when it got to those standards committees to have a company name on it, so it got renamed as SCSI. He can define what that's all about. SCSI evolved. It's gone through many evolutions, and today it's the most widely used disk drive interface on the disk drives attached to all those computers in the storage world today, along with fiber channel and a growth of the simpler ones called serial ATA, but SCSI is still the name of the game. And, of course, farthest to my left is Randy Katz, UC Berkeley, distinguished professor in electrical engineering and computer science, co-author and leader of the original 1988 paper on, quote, redundant arrays of inexpensive disks. The acronym, of course, is RAID. And those of you who have toured downstairs have seen the prototype of what they did to prove all out that it worked. We all know that disk drives occasionally fail, especially when you've got a computer room filled with hundreds of them. And, of course, if you've got hundreds of computer disk drives and they have a MTBF of a million hours, well, okay, divide a million hours by 100, you come up with the average amount of time in that computer room you might see a disk failure, in theory. Well, the RAID systems developed a way to protect against failure by being able to recover immediately from any individual drive which did fail. I'm sure he'll tell you about some of that. So to get started, I'd like first of all to ask the gentleman immediately to my left, Mike Gluck, to come up and give us some of his ideas on the history of that evolution and how it occurred. Mike?
Thank you, Jim. Thank you, Jim. It's a pleasure and somewhat humbling to be here and talk about the disk drive industry, something that's grown into a $50 billion business over the last 40 years. This is the first disk drive that Jim talked about that he saw. I was 10 years old, so, so I never saw this disk drive, so I had to copy this out of a book. But this is the Ramac disk drive that Jim talked about. Jim said he started at Memorex in 1968. That's when I started with control data. Graduated from the University of Wisconsin and spent the first year or two maintaining large computer mainframes. And then I got into the disk drive industry in 1970 in the IBM compatible world, and so I've been doing it ever since. So that's the last 35 years. Control data, as Jim mentioned, is one of the pioneers in the disk drive business, and its claim to fame was really in the OEM business. The IBM compatible business was about $150 million business, but Control Data started selling disk drives to those companies in the 128, to DEC and Data General and Prime and people like that, and that business became $1 billion and eventually a $2 billion business, and it was 40% of Control Data's revenue and about 2/3 of profits. This is a little bit of the history of the drive. So here's the Ramac in 1956 at a cost of $7,800 and 5 megabytes with 24-inch platters. And this is the access time, that's the seek time. The latency is obviously the amount of rotational time, and then the data transfer rate to transfer that data. And you can see what's happened here with the 2314, 3350, 3380 over the last years, and the platters becoming smaller, 14-inch. The Eagle disk drive, when I was at Fujitsu, 10.8-inch, somewhat non-standard, but then 5.25-inch and 3.5-inch. And so I put out here in 2005, because I hadn't updated this slide since 2000 here, so this was really Fred Moore's slide. So here we are at about 5 cents a megabyte and 300 gigabyte drives. So you can see the prices have come down an average of about 30% a year, and the technology has continued to improve. And this is a little bit of the technology. If you look at the year it was introduced, the time it took to service a request, and then how many IOs per second could you get out of that disk drive. And although the capacity has gone up, the what's called the access density has gone down, because computers have become faster. So how many accesses per second per gigabyte has continued to go down. And so this is one of the challenges in the industry and the reason for network storage and other kinds of activity. And then so here we are with SCSI, fiber channel, SATA drives now, 6 millisecond access time, 300 to 400 gigabytes per spindle. And the technology, and I'm sure this is old news for everybody here, but is really the areal density is a measure of the figure of merit. And this is a disk platter, and you'd have the number of tracks per inch times the number of bits per inch. And so if you look at the areal density, it's really continued to grow up. On a logarithmic scale, it's really linear. So if you look at this areal density and the types of technologies that have occurred over the years, from ferrite heads to thin film heads to MR heads, and this is technology has gone up on an average of about 60%. In some cases, it was going up 100% per year, but it was started out about 40% per year, and now we're still seeing about a 50 to 60% per year increase. So the other part of technology is if this is a platter, and if you could think of this spinning platter that they started out spinning at 3,600 RPM, and now we're 5,400 to 7,200 and 10,000 and 15,000 RPMs. And the read-write head, the magnetic read-write head, is still flying off the surface a few millionths of an inch compared to a cross-section of a human hair. So these disk drives are all assembled in clean rooms that are cleaner than the hospital rooms, and because smoke particles, even a smoke particle would cause a head crash. And so to me, it's always been amazing how this technology, and somebody made an analogy, actually Richie Larry from Digital made this analogy that the technology of disk drives today is equivalent to you and I being a pilot of a 747 flying at 1.5 million miles an hour at a 1/50th of an inch off the ground, and then you're looking out trying to read the dominoes as you're going by. And it's an incredible technology feat that, when you think about it, and for that technology to be increasing at 40 to 60% per year has really been amazing. And, why do you need all this capacity? And who's really using all this? If you take a text page, it's 2,000 bytes, 2,400 bytes on a page. A byte being a word, so 2,400 words on a page, if you will. And that's going to cost you $25 per megabyte. If you add up all the cost of the paper, and that's really what you're paying for. And a terabyte of paper, so you have megabytes, gigabytes, terabytes, so 1,000 gigabytes. That, by the way, that just costs 42,000 trees to generate a terabyte of paper. We were supposed to go to the paperless office, and now we're killing more trees than ever. But if you look at images, 38 megabytes for a high-resolution color photo, 200 gigabytes for a 2-hour movie, 22 megabytes for a telephone recording. It's now estimated that the average person will accumulate a petabyte of data over their lifetime. From, if you think of the photos of your kids, the videos of the soccer games, and everything else. So you're going to need a petabyte is 1,000 terabytes, which is 1,000 gigabytes. So if you've got a 200 gigabyte drive, you better have a pretty large basement to store all those drives if you're going to be a petabyte. And that's really what's been driving the technology.
Does that include spam?
Yeah, if you include email spam, it's going to be 4 to 10 terabytes, so 4 petabytes. So thank you very much. And with that, I'll turn over the speaker to Claude Barrera.
First of all, let me explain my trepidation in giving this talk. As a strategist, you spend almost all of your time forecasting the future, and almost none of your time explaining the past. Much less to an audience that may understand the actual past better than you by having lived more of it than I have. So we'll see how we do. As sort of partially as a self-defense mechanism, I've picked a particular thread of the entire span of the storage industry, and one that I think I can speak to with maybe a little more personal experience than all the rest of it. And the other that might be, or at least I have a point of view about. So the case I'm going to make is that there is a particular class of machine that most people have no idea exists, but in fact is a fundamental piece of infrastructure of the world that we all depend on and live in and like to have. Most people will never see one. I believe probably a lot of people in this audience either designed them or worked on them or knows a lot about them. So we'll see as we go. But I believe it's kind of an interesting thing to know what the physical world around you really is. So let's see how we do here. We're not doing very well.
Down, down.
Down?
Yep.
There we go. Okay. So let's see. This thing is also, oh, good. It's a pointer too. So the first picture I've got over here, this is a mainframe picture. And as you can see, we've spared no expense in the level of detail of these pictures. But what's shown here in concept is a mainframe. So that's the processor there. And here are all of these terminals that people are doing TSO kinds of things, or computing of that ilk. And then over here, you can recognize these things. I mean, cylinders are always disk drives. And then there's this other curious box here. So we're going to talk about the evolution of this thing. So this is the humble beginnings picture. And in the beginning of, say, System 360 and System 370, these strings of disks, or DASDs, were relatively large things compared to the mainframes they were attached to. Consumed a lot of power, etc. And there was this necessary evil in here called the control unit. And the purpose of the control unit was to switch whatever drive happened to have the data that you were interested in at that particular moment onto some kind of bus that then spoke across an OEMI channel to the mainframe. And everybody that sort of knew how these things were done would say that all the real engineering and real science and real value and real work happened over here in this string of disks. And this thing over here was a funny wide spot in the cable that wouldn't be there at all if the electronics were cheap enough to where you could have one of these connections for every one of those disks. And the curious thing that's happened in the last 30 years is that this box over here and the things inside it have become relatively small and relatively commoditized. And all of the real business value of high-end storage systems is actually living in boxes that are the proper descendants of this necessary evil. And if there are people whom I know and love and worked with in the mid-'70s when I first joined IBM that would be apoplectic if they understood what was going to happen. I mean, hopefully they're all deceased at this point and don't have to live with this. But there was actually, professional rivalry, and people were accused of trying to put function in this box. People would be chastised for trying to build control unit empires. That was a term that got thrown around if you were unnecessarily doing engineering in the control unit. So the next step, and this was another one of these necessary evil things, that the system structure of the early days of MBS was such that these servers or these mainframes wanted to share storage. So a picture like this was then necessary. So you had to be able to connect multiple mainframes to the same disks, and software was worked out so these guys could share disk capacity properly. And this was all done from the standpoint of making the overall applications more highly available and more scalable and run faster, et cetera. So this was another necessary evil sort of step along the road. So by now we're sort of even out into the maybe the mid-'70s. So IBM is developing these kinds of products, as are the JCMs. The next sort of funny little trick that somebody thought of to put in here. People in research were working on this. In fact, there was a skunk works in Tucson that had anybody actually known what was being done, the people involved working for Billy Joe Mooney probably all would have been fired. But they were putting read caches in this control unit. And Memorex had the good fortune to be doing the same thing and came out with a product, and suddenly a competitive force made the necessary evil of this control unit a thing that we had to deal with inside of IBM. So suddenly we had the Sheriff and Ironwood projects done out of Tucson that were basically caches in front of or as part of this control unit. The next step that happened is we attached these control units to still mainframes through a switched fabric. The first fabric for us to do that with was ESCON. Now you're starting to have sort of bigger and bigger capabilities inside these control units, real computers with caches, and some real malcontent invented something called fast write caching, where when you did a write to this box, you actually wouldn't write the data all the way to the disk. I guess I've worn out my wall. Oh, there we go. You actually wouldn't write the data all the way to disk before acknowledging it to the system. So you were lying. You said the write was complete, and it really wasn't. Only this funny control unit actually had the data. And there were all kinds of predictions that this would be terrible, and in fact it was wonderful. It speeded up performance, and all of us did good things with it. In parallel with that, there was a need for software to manage these things, because the capacity was becoming bigger and bigger, and the dependency on its proper management was becoming higher and higher. So some folks here in San Jose went off in IBM and developed this thing called System Managed Store. DFSMS was the acronym for it, which included hierarchical storage management, backup, and recovery, and device management. So the phrase that everybody used to pummel each other with was, the cost of storage management exceeds the hardware purchase price by a factor of, and then you added your integer number here. And there actually was one study once done that claimed to figure out that this number is 8. But when you actually try to get a copy of that study, it's elusive. But the interesting thing about DFSMS was that they actually had this notion of automating the role of the storage manager through something called policy-based management, which is a marvelous term, and everybody uses it today. And they introduced the notion of data class, which said, here are the characteristics of the data. Here is what needs to be true about how the data is stored. And the notion of storage class, which says, here are the characteristics of the storage itself. So you try to match those things together in an interesting way. And if you do it properly, then good things happen. So this is the first instance where somebody other than the first-line manager, storage administrator in a customer office actually knew about anything that was going on in storage. Nobody, CIOs and CEOs never talked about storage. We went through an evolution, and I'm sure some of the other speakers will talk more about RAID and small form factor disks and really big caches, and we took the ESCON fabric and we created a similar one based on the SCSI protocol that Larry invented. So now we had the ability to connect these bigger and bigger boxes to lots and lots of not only mainframes but other types of servers, Windows servers and Unix servers, and the relative size of these control units is becoming large compared to the size of the disks themselves, and they're learning to do more and more fancy function. But the really salient event, there was a thing happened in New York City in the summer of 1993. And that was a bunch of people tried to blow up the World Trade Center. Now, they didn't succeed in doing enormous amount of damage. They did actually close the buildings for several weeks in the case of one building. But there was an interesting debate that ensued as soon as that event happened, and basically went along the following lines. What would happen to our data center if it blew up? And the people having this discussion are all the banks and all the brokerage houses, because they were actually themselves directly affected by this event. And overnight, there was a critical need for new functionality in the storage world, and that was the ability to real-time mirror the contents of this storage device over here, which is the ultimate repository of all these wonderful business transactions that are going on, which, as we know in the financial world, equate to real money. The need to have a real-time copy of that same stuff somewhere far away. And far away, in the case of New York City, meant in New Jersey. It had to be a power grid away. Other side of the river was okay. But what we were really worried about was the building blowing up. Now, if the financial capital of the world had been in San Francisco at the time, maybe far away would have been further. But then a bunch of very smart people at EMC put two and two together, and they said, here's a need. Here is a place in the world where we can do innovative development. We can create something. And what they created was a product which is now called SRDF, Symmetrix Data Replication Facility, which basically says that when an I.O. is received by this box over here, it can mirror that write to a remote box somewhere reasonably far away. And the reason this is such an important event is overnight, the need for this kind of function was understood by CEOs and CFOs, and they sat down in their boardrooms and had discussions about how they were going to solve this problem. And almost for the first time, the storage guys came in as the people with the answer. And it's basically been that way ever since. There's been some other things invented. So there's another model. We've been talking about block storage, but these things are file servers, so we can serve files across IP networks. Auspex here in the Valley did some of the original work, and of course Network Appliance and EMC are the big players in this today. There's a whole range of capabilities that these boxes have to have. Manageable, reliable, available are the things that grew up out of the mainframe world. The new ilities deal with the question of, if I'm going to store all my business data, all of my business data, including all the spam that comes in from wherever, what other kind of capabilities do I need? So you need to be able to be flexible, scalable, open. You want to connect lots of things together. Increasingly auditable is a really good one. Secure is going to become a very important one. There are still layer wars going on. Just as we had the debate inside of IBM about, is this thing a necessary evil, and is the right amount of work to be spent on this something close to zero, or should you pour a lot of money into this? The real issue going on in storage today is, of all the places that a certain function that a customer needs could be placed, where should it be placed? And the interesting fact, or the one message that I'm trying to leave you with, is a bunch of really entrepreneurial people taking advantage of the fact that there is not a single common storage or common usage model for storage, took upon themselves the goal of capturing need and bringing it into their layer. And as a result, they have built up ever-increasing, ever more valuable, ever more important products that contain more and more of system functionality. So that's probably a good place to stop.
Thank you. Next we'll have Larry Boucher with a few words. I'm not sure when I mentioned what Larry had done with SCSI, I'm not sure I mentioned that he, of course, started a company to make the controllers for the SCSI product, called it Eptech. And you just heard a mention of a company named Auspex. Well, he also founded that company. And, of course, he's now the president of Alacritech. Larry, why don't you explain what the heck you were doing with all of this?
Thanks, Jim. I don't have any pictures of any of the things that I'm going to talk about, so I figured I'd just talk. And really what I'm going to do is just go through what are the things that I think have been the major technical innovations that have made a real difference in our market, in the storage market. And the first one was the 3330, which was the first voice coil actuated disk drive. Before that, believe it or not, disk drives, well, many of you already know it. In fact, this is one of the intimidating things is talking to you guys when most of you know more about this than I do. In fact, last night, I had the misfortune of meeting up with Jim, and so I reviewed what I was going to say today, and, he kept correcting me all the way through. Anyway, so I think that, going to a voice coil, which was a long time ago, and yet, that's still the way we're driving disk drives today, was a major change. Then the 3830, which Claude just mentioned, the Mod 2 3830 was a major change over the Mod 1. The Mod 1 worked by putting a SerDes and a VFO in front of a very fast bipolar processor, putting a lot of memory in it, costing a fortune, and running the entire data stream of the disk drive right through that processor. The Mod 2, which was, as far as I know, Abe Gindy's concept, took the whole data path and put it in hardware so that the processor could now be much less expensive. Now, because it was just a Mod 2, we use the same processor. So we didn't get a big cost reduction in the first version, but from then on, controllers got a lot less expensive because we had taken the difficult part of the job and put it in hardware. The next thing, and I mean, if Ken Houghton is here, I don't know why I'm talking about this, but the next thing was Winchester technology. And Winchester technology, I'm sure you know, got generated because the product that was going to be built was going to be 30 megabytes fixed and 30 megabytes removable. The real technology has nothing to do with a fixed or removal, right? It has to do with the fact that up until then, disk heads couldn't load on the disk. So you'd spin the disk up to speed, and then you'd move the heads out and let them fly on the disk. Well, what Ken did was say, well, you know, let's save all the cost of having to separately load those things and just have the heads land on the disk and then take off again. So that was a major change that got us to the next level of capacity and cost reduction. The next one was the 3350, and that was sort of an interesting product because, in fact, you know, I don't know what the story was. You know, the original Winchester product never happened, right? The 3340 was just a removable product because there was a religion inside IBM at the time that said you can't have a fixed disk drive. It has to be removable. And in fact, the 3350 had major arguments for a long time about whether it was a real product at all because of the fact that you couldn't remove the disk pack. Sort of ironic if you think of it now. And in fact, that product sat 2 years after it was finished. It still hadn't shipped because at the time there was a project going on in IBM, maybe some of you have heard of, called FS, that was taking every single programmer cycle in the business. And we had 7 operating systems at the time that we had to support before you could ship the disk drive. And it was about $1 million an operating system, and the number of people that it took to support each one of those operating systems, there were no programmers to do it. So this product, the 3350, sat on the shelf for 2 years. When finally, you know, we realized, gee, you know, we better make some money somewhere. FS wasn't going so well. The product became the top money maker for the company, and those that had a religion that said it had to be removable changed their religion. The next thing, and this is, you know, I mean, I guess I have to, I'm not trying to toot my own horn, but I think the next thing was SCSI. We built SCSI, and a couple of interesting things about that. It was SASE, Shugart Associates Standard Interface, and that name was already taken. There was a guy, Rich Steele, actually building a new interface for our disk drive, and he'd chosen Shugart Associates Storage Interface as the name of his product. And I fell in love with it. SASE was a great name, so I tried to figure out, okay, what can I do? And I traded him SADI, which he liked also, for device interface. And so I managed to convince Rich to take SADI so I could have SASE. And And then, of course, ANSI, as Jim was saying, wouldn't let us have a company name in the name of the interface. So we had to change it. And we had almost a full day discussion on, okay, so what are we going to call it? So finally we decided small computer would work, small computer system interface. And I was praying that sexy would go. Dal Allen walked into the room and he said, oh, SCSI, and it's been SCSI ever since. So. Anyway, the whole reason for that was it was taking us over 2 years from the time we came out with a new disk drive until it was integrated by the customer, because the interface was different every time. It was a low-level interface. So by defining an interface that was a standard, you could now come out and instead of 2 years, in as little as 6 months, the customer could integrate a new disk drive. Previously, you know, the computer was built, it went with that disk drive, and then they never put another disk drive on that computer. Now, suddenly, we could sell a new disk drive into the same computer system. So it allowed the disk drive industry to move much more quickly. And that was really what we were trying to achieve, not what actually happened. The next thing, from my standpoint, was what we did at Adaptec, which was to copy what IBM had done 12 years before, but instead of putting it in a big box, you know, that box that Claude was drawing, we put it on a single chip. And so we basically, the industry was still doing the same thing in the controller industry. You'd use an 8x300 or a bit slice and a lot of bipolar memory. It cost a lot of money to build a controller, but it made up for it by taking 2 revolutions to read a track. So, so by putting it in hardware, we could get the cost way down and read a track in a revolution. I think that, and if you talk to anybody in the storage industry, they wouldn't consider that you could do disk protocol processing in software. It would be a joke. We're trying now to convince the networking guys that that's true too, but another story. The next major change or stochastic shock to the industry was IDE. That was a particularly big shock to us at Adaptec because even though most people thought we were building SCSI, really we built the company to around 100 million or so building disk controllers for IBM PCs. And then IDE came out. That was, Finus, Connor, and Compaq decided to build this new interface, integrated drive electronics, and we were toast. Within a year or two, there were no more disk controllers. So we had to come up with a new thing, and IDE made a big change and cut the cost of disk drives, so we had to come up with a new thing called a SCSI HBA, which brought SCSI back to what was supposed to be originally, a channel interface, not a device interface. And SCSI from now on and then Fiber Channel after it have been purely channel interface. Well, pardon me, Fiber Channel tried to be a device interface, but it's really a channel. The next major thing, and I think this is one of the biggest ones, Randy hopefully will talk about, and that's RAID. That really changed the industry. Up until then, you had disk drives that broke, and we kept worrying about how you would, fix them so they wouldn't break so often. We did defect skipping, then multiple defect skipping, and all sorts of things to try to make sure that the disk drive would continue to live, but it's a bad device. They just break. And so RAID was a fantastic solution. It not only increased the performance significantly, but it allowed you to really know that you were going to be able to get your data back. Next thing, I think, was what we called network-attached storage. Sun came up with this interface called NFS, which was a really exciting interface, so we decided, well, let's use that and build a specialized piece of hardware that really just does NFS. And that allowed the whole network-attached storage industry to get started, which now has become a significant part of the storage business. And the last thing on my list is Fiber Channel. Fiber Channel itself allowed the whole storage area networking business to get started. And if you look at where we've come from a storage standpoint and what it means from a storage subsystem standpoint, storage attached, storage area networks and network attached storage are the really 2 fast-growing areas in the storage business. So those are the main things that I think have happened over the last 20 or so years.
Okay, Larry, thank you. And he's mentioned how a lot of these standards, which are very important for a lot of companies to participate equally in the industry, occurred. And one of the most important sets of standards in the world, of course, is RAID. And there's the guy who was key to doing it. Randy.
Thank you, Jim. Hopefully we can get this mic going. Thanks. Wonderful to be here. Wonderful to be on the stage here of the Computer Museum, Computer History Museum. This is a little bit of a personal tour through I was describing it to one of my colleagues up here on the stage of the one time in your career where you get to hit the grand slam home run at the bottom of the 9th inning in the 7th game of the World Series, which is to develop this concept of RAID and popularize it and have it have such a huge effect on the industry. So I've titled the talk, RAID and Me, or How Storage Became a System, or at least as a computer scientist views a storage system. Those are some of the prototypes that we built, and it's been pointed out that the one on your right is available in the visible storage in the museum itself. So my personal recollection, the first kind of genesis of the ideas relating to RAID, I had returned to Berkeley as a faculty member in 1983 from University of Wisconsin and was working on a paper with Mike Stonebreaker and a cast of characters that are shown here on this slide. I went wild searching for images on the internet using the A9 search engine image capability, found everybody that I was looking for, but it was a paper on how to design main memory databases. I had done my dissertation in database technology, and we were trying to figure out how you can make databases go blindingly fast, how you could do thousands and thousands of transactions per second. What was the ultimate bottleneck for that? And we came up with all kinds of clever ways of doing query processing, log management, group log writes, all kinds of things. But it ultimately came down to the number of log writes you can do per second. And as has been shown in one of the earlier slides, no matter how good a disk is, it still does about 50 IOs per second max. In fact, they actually got slower in the recent technology. So you could be very clever about what you're doing and group together all sorts of transactions and delay their commit, but when you commit them, you have to do an IO operation. You can do 50 of those per second. And so that was sort of one of the bothering factors that left me after we had done this paper, and it sort of was rattling around in my brain for a couple of years, actually, of how to deal with this log write bottleneck. The second major thing that happened was in 1984, won't be like 1984, the Macintosh was very exciting for us in universities. We all went out and bought one. For some reason, it was a lot more interesting to us than the IBM PC of a similar vintage. And somewhere around 1986, the Mac Plus came out with a SCSI interface on it. And this meant that you could put a serious amount of storage on your personal computer, 10 megabytes, let alone that it cost $2,000 for that little box that sits underneath there. This was fantastic. And I kind of remember in 1986 looking at this thing and saying to myself, gee, for $2,000 I can buy a pretty cool disk. Maybe it can only do not 50 IOs per second, but 30 IOs a second. But, gee, maybe I could buy like 100 of these, and it would cost as much as that big mother IBM disk, and it can do 100 times 30 instead of only 50 for about the same price. And we started thinking about this sort of idea. So SCSI, the low-cost, small form factor, led to the idea of maybe for the same amount of money you can buy a bunch of these and put them together in some way. But the second you start thinking about that, you begin, just like in semiconductor memory systems, lots of components together. They have independent failure modes. They're going to fail at some rate. Whatever that rate is, divide by the number of components you have. And now this fantastic silver lining starts to have a cloud. Namely, a room full of disk drives are going to have a lot of broken disk drives. So we started trying to think about how to build redundancy into the system that will go beyond the redundancy which is inherent in disk drives already, the ability to have its own vertically recorded on the disk drive error correction. There's a wonderful, rich technology that's been developed in the disk drive industry to deal with that, as Larry mentioned. So somewhere along the way, my colleague Mike Stonebreaker, who had also participated on a panel like this at the museum a couple years ago about database stuff, led a project called Express. It was an extensible database system. It led to a project called Postgres. But the main thing about it was we were trying to marry database technology to multiprocessors so that you could have a database system that could talk to a system with lots of processors and lots of disk drives in it. And we got good funding from National Science Foundation to do this work. But if you go back and look at that proposal, there's nothing about RAID in it. We hadn't really had the idea of that we needed redundancy or how to build the redundancy into the storage system in support of the database. But we knew we wanted to harness a large number of disk drives to a database to get good database performance. So during the summer of 1987, sitting around, like academics do, eating lunch, talking about things, Dave Patterson and I came up with this idea of, we really need to do something about the reliability of building systems that have large numbers of disk drives. They're mechanical gadgets. They're going to fail. They're going to have some failure rate. And Garth Gibson was a graduate student working with Dave at this time. And it's one of those things where this is what we're thinking about, Garth. Go off and make it happen. Find out about how we do reliability in this sort of environment. How do you analyze it and so on. And that led to one of those really intense periods in a researcher's life where every day we'd come back with some new idea that had come up in the last 24 hours when we got together the next morning to talk about it. It was a very rich time for us, and Garth's dissertation eventually did win an ACM dissertation honorable mention. Well, during the fall of 1987, that's right after that summer, we started developing this idea of the RAID taxonomy. And during the beginning part of that, our old friend Al Hoagland, who's another one of these godfathers of the storage industry, I'm sure many of you know who he is, Garth and Dave took one of his short courses at Santa Clara University, and they learned everything you could possibly imagine learning about ECC and error correction and error recovery and the mechanics and the physics of disk drives and flying heads and all that kind of stuff that Al was a real expert on. And from that, that led to a knowledge of various ways that people had built redundancy into storage systems already. Tandem in the 1970s, early 70s, had come up with the idea of mirrored storage, copying things in two places. If one place fails, you always have a nice copy in the other place. Through some consulting that Dave did, he was aware of work that was going on at a multi-processor, aggressive SIMD type machine, thinking machines. At the time, it was an SIMD machine. And they had built a storage system that was a bit serial, serial access, bit parallel, 32-bit word spread over 1 bit on each of 32 disk drives and then streaming to them, storage system to go with their SIMD parallel processor, and it was called the Data Vault. And so we understood how they organized it. They basically did the same thing that a memory card would do in terms of Hamming codes computed horizontally across the memory bits. They did the same thing on the disk drives. They had bits stored bit per bit on the disk drives, and horizontally across them they added some more disk drives and computed a Hamming code in the word position across each one of them. So we decided if mirroring is number one, then this Hamming code idea is number two. Don't ask me why we came up with, numbering them instead of giving them names, but that's what we did. And then somebody told us about this drive that was coming out of Silicon Valley that was 3 disk drives and a 4th drive with parity on it. Well, parity is a sort of poor man's version of Hamming code, and since disk drives know when, you can tell when a disk drive is dead because you try and talk to it and it doesn't talk back to you, thanks to high-level interfaces like SCSI. You don't have to do the thing that memory chips do where you read it and junk comes back as opposed to some indication that it failed. So you can get away with a much simpler scheme for redundancy based on parity. And Micropolis was, to my mind, the first company that tried to do this. So, gee, this is another new idea. Let's call it RAID 3. And there were lots of other ideas about taking data up, breaking it into pieces, interleaving it. The database guys called it declustering in database machines. Supercomputing people called it interleaving of files across this. So we sort of knew about those things. And we took the parity idea from RAID 3 and the interleaving ideas and came up with this RAID 4, RAID 5 type schemes. RAID 5 with rotated interleave parity is the scheme that's generally used in RAID systems today. Now, probably the most exciting month in my entire technical life to date was this tech report that we wrote, A Case for Redundant Arrays of Inexpensive Disks, known as the Patterson et al. Paper, and I'm often referred to as Al of Patterson et al. Never, if you have a chance to write like a really influential paper, volunteer to write it so your name gets to be first. Big deal. So what we tended to do when we wrote these papers, so this was based on all those discussions from the summer and early fall. We wrote it up. We felt we had reached a level of maturity with it to kind of, put it down on paper and claim the ideas and start to get feedback from people in industry about it. We had sent a copy to our friend Jim Gray, who's one of the geniuses of databases, to get his feedback, and he came and harangued us and told us why we were doing it wrong and all kinds of things like that. We also sent a copy to Al because Dave and Garth had just taken the short course from him. And little did we know, but Al is the center of a social network of everybody who's anybody in the storage industry. And what Al did was to send a copy of our paper to everyone he knew who he had heard was working or thinking about doing multi-disk systems. So before you know it, that little thing on the side is a scan of all of the little telephone message sheets we started getting from people, from Control Data, from DEC, from Sun, from this company and from that company, who were working on multi-disk systems and read this paper and wanted to talk to us. about it. So this was one of those magical times with the arrival of SCSI, small form factor disks, and a lot of people in the industry coming up with the idea of there's got to be a way to put lots of disks together in a box to get high performance. We know there's going to be a reliability issue. We need to do something about it. They're all kicking around these ideas, and this paper lands on their desk, which is a taxonomy of the different trade-offs and ways of doing it. Boy, were we born on a lucky day. Because this is what they needed to understand what they were doing, to put a common language and common vocabulary around it so that the field as a whole could move forward. And everybody was doing their own thing, had their own names for it, but now there was a context that allowed this to develop unbelievably rapidly. And I think that's why RAID really took off in the time frame of the late 80s, early 90s, because of this nomenclature that came out of this paper. The technology was running around already. Lots of people were thinking these thoughts, but having a common language made a huge difference in the ability to advance this field rapidly. Oops, wrong way, sorry. Now, Bruce Lindsey's in the audience. I didn't know he was going to be here tonight. He played an important role in this. We submitted the paper to the SIGMOD conference. It appeared in 1988. At the time, we thought we had invented RAID 4 and RAID 5, RAID 5 being the rotated parity scheme that's commonly used. Now, as academics, we didn't spend a lot of time reading the patent literature or doing patent searches. Today, people and companies do a lot of that sort of thing. And in the latter part of 1988, I went to IBM San Jose, also known as Hitachi San Jose today, to give a talk on RAID technology. By the way, I was scared to death to do this. Dave Patterson had told me about some of the risk talks he had given where he was, they pulled his fingernails out when he went and talked about this stuff in front of Intel. And I thought, here is Mohammed going to the mountain to tell about this other way of doing storage. I'm going to just get run out of town, tarred and feathered on a pole. I'll never be able to talk again, something like that. And the people at IBM were incredibly gracious. Their questions were good questions, probing questions, but also friendly questions. And I remember one guy saying on the way out, well, I guess that's just another nail in the coffin of IBM or something like that. They were resigned to the inevitability of this in a way that at least I felt pretty okay after that. But Bruce was in the audience. He comes up to me afterwards and says, Randy, your talk was very interesting, but do you know about this thing about AS400? There's a patent that's just come out of how they do protected memory in the AS400. Well, I don't know about that. And I think he gave me a copy of the patent, or there had been a big study in IBM on how to accelerate these parity calculations that Bruce was aware of. So we went back and we looked at the literature, and sure enough, it's like, on the original Star Trek, everything was invented by a little old lady from Leningrad. That's what Chekhov used to say. Well, my God, there's this Uchi patent from 1978 that talks about essentially a RAID 3 that was developed at the IBM Palo Alto Scientific Center that was related to some of these issues about how you would build non-removable storage. Some clever ideas for dealing with the fact you're not going to be able to take it out. What happens if it fails? So Uchi had actually come up with this idea of parity not interleaving, but parity on a separate device that's very similar to the RAID 3 organization. And you know how patents are. You could read into them all sorts of what the word of God really is in this, what do they really mean, and maybe had the ideas for the whole RAID concept in there anyway. And later on, the patent that Bruce had brought to our attention was the Clark patent, which is really how the AS400 was doing it, the read, modify, write, parity scheme, interleave, rotated. It was all there. It was all there in that patent that was filed in 86 and was issued in August of 1988. So a lot of these ideas were floating around at the time. The key thing, again, was the nomenclature, the common language, the common vocabulary that allowed the field to go forward. So another important thing to mention, my colleague John Osterhout left the university for an industrial career, and his student Mendel Rosenbloom, who's a professor at Stanford now, who also won the 92 ACM Dissertation Award. RAIDs really stink for writes, especially small writes, and I want to really give credit to the software guys for developing a write-optimized file system that turned that write penalty into an advantage for RAID systems, and it just goes to show some of the importance of software meeting the architectural concepts. The system, you can go see it in the visible storage. We worked in developing it with DARPA and NASA. It really was a network-attached storage system because it was on Ultranet's network, which was essentially like the storage networks that have been mentioned already in some of the prior talks. It was based on a fat cable technology called Hippie, as opposed to fiber channel, but it really was like that. It was a file server attached over a network with a fast, high bandwidth path and a slower Ethernet-based control path with this optimized file system. So it was a very interesting, complicated system when you put it all together. Lots of disk drives in a small footprint for its time. So when you really think about storage as a system, there's all of this logical to physical block mapping. The storage is virtualized. You have a picture of it as a logical sequence of blocks, but it's in fact spread and interleaved over all kinds of complicated things. You have to deal with the striping and the placement of parity, the read modify rights. Rights are not rights. You actually read some old stuff, make some changes to it, and write it back. Getting complicated. There's all these caches, and you have to orchestrate the data staging between the caches and the disks and back again. This is complicated. You have to understand file server protocols, NFS, file server interfaces. It's complicated. What happens when a disk fails? You have to identify the disk has failed. You have to rebuild its contents, restructure it from the redundancy that's in the system to a hot spare. You have to deal with hot spares. You have to let the operator take out the broken disk and put in a new one. You have to copy the stuff back to the new one that's been put in there. Complicated. With this log-structured file systems, they're complicated to understand how to implement. Compression on the fly. That was another innovation of when you write things, you have to compress them. So the key point here is these are complicated systems, probably more complicated than the storage system architects had been used to because of the huge amount of software embedded in one of these things. So just the last slide, the legacy. If you Google the term RAID, of course that also is a bug spray, but you get 11.1 million hits. If you say Berkeley and RAID, you get only 159,000. The original paper is number 539 on the hit parade of most cited papers of the 100,000 or so that are indexed by CiteSeer. It's a huge industry. And I believe that the IBM web page definition of RAID is very appropriate. When you look under the RAID levels, it calls them the Berkeley RAID levels. It gives us the credit for the terminology, the way of looking at the trade-offs between performance and redundancy within disk systems and giving a language and vocabulary to that. And that really is the contribution that we had from Berkeley. Thank you.
Well, in a few minutes, we'll open up for questions from the audience. But I have one for our group. You know, just a couple of days ago, the market research firm IDC published their numbers on the overall 2004 total storage system shipments worldwide. And you know what? They pointed out that only about a quarter of that total revenue was coming directly from drives which are directly attached, systems in drives which are directly attached to computer systems. More than 75% of it is now coming from independent sources. How do you account for all of that? Is it only from these standards that we've seen created here that were mentioned? Who has a comment?
Well, let's see. If I understand the statistic you just quoted, you're saying that 75% of storage or server class storage is attached via a network of some kind, and that's actually by far the dominant attachment today, and it'll continue to squeeze out direct attach. The fact that you can have independent storage boxes that are highly reliable, that allow customers to install storage capacity and then sort of as needed assign it to individual servers or individual applications. That actually is the way customers think about storage today.
Mike, you're a participant in that market. How do you get your business?
We are a network storage vendor, so we are selling storage. The two types of network storage are storage area networks and network attached storage, but it's basically putting disk drives on a network. And the network attached storage is you access them as files, and storage area networks, you access them as blocks. And I believe that the reason for the 75% is because of the statistic that Claude mentioned, is that the cost of managing the storage is, we use 5, okay? 5 to 8 times the cost of buying the storage. So for every $1 per megabyte of hard disk drives that you buy, you're going to spend $5 per megabyte per year. And the only way to reduce the people cost is to consolidate the storage and use management tools. And if you've got storage on this server and storage on this server and storage on this server, it's just too complex and too expensive. So it's really the industry's response to trying to address the management of storage. And that's what's driving the network attached storage.
Any other comments? Okay, well, I should just interrupt, I think, to mention that Claude and Larry and I were attendees, and these two were speakers, at the Network Storage Conference, which is just finished as of this afternoon, but it went on for the last few days. I made a note of what I thought was the most interesting statement by any of the speakers at that conference, and I'll attribute this to Claude Barrera.
Uh-oh.
All hardware eventually fails. All software eventually works. A brilliant set of
But not if it's written by Microsoft.
So the context for that remark, it's an argument for managed redundancy. You can't build highly reliable systems of the kind that we would want to be running the air traffic control system or the banking monetary exchange systems. You can't do that by relying on parts that never break. You have to do it by building up aggregations of things, each one of which could fail, and then of course you have to have software that keeps track of which ones of these are dead and what to do when one dies. But the warning is that don't expect these things to happen overnight. You can draw these nice pictures and show all this nice redundancy, but it takes a while before that software is perfect, just as it took us probably, 3 or 4 years after the RAID papers were written before we had real working products that you could walk up to and yank a drive out of and everything kept going.
Was it years before we had RAID systems that really work?
Well, years after the Berkeley papers were published, yeah.
What do you say about that one?
I think that's true, that it does. I think it's amazing that you could have a university paper and only 4 or 5 years later have practical products that are based on the ideas in that paper. So I think that's a fantastic horizon between concept and working system. The reason I had that slide with storage as a system was getting all of those things to work reliably as software eventually working, and doing it efficiently and all those other kinds of things. Especially, one of the things I observed, the Storage Tech Iceberg product for mainframes attempted to do many of the things that were on that list. It took them an awfully long time to get the, quote, firmware correct, because they were writing zillions of lines of code to do all that functionality. It is a complex job for people with an original background that were not building operating systems before. They were building firmware for disk controllers, which is a tremendous technical challenge, but it's not at the level of millions of lines of complex system-level code, as was starting to be introduced with things that now had to talk file server protocols and all this RAID concepts and things like that. So it was, I think, the 5 years was the quantum leap in software complexity to get these systems to work. And one of the bullets I had on my last slide was, today, software RAID is a standard module in Linux. So we know how to do that kind of stuff today, but there'll always be the next wave of complex functionality like distributed redundancy or that kind of thing, which still will require some period of time to understand how to really make it work.
Well, in Randy's slides, he showed a few which had a string of disk drives behind a big controller. And many of us who remember what computer rooms looked like in the old days, the old glass houses, which were filled with what we called disk farms in many cases, with literally hundreds of disk drives, typically 8 drives behind a controller in that 360 world. Larry, wasn't one of the key things that came along with SCSI the ability to embed the controller functions within the drive?
Yeah, that was one of the things that, even though we were building an interface we thought was a channel interface, we wanted to get it down to a single drive initially. And in fact, that was one of the first things that we worked very hard on at Adaptec, was to sell the disk drive manufacturers the silicon to build SCSI drives. And it took a while. I mean, I would say it took 4 or 5 years, but after 4 or 5 years, we initially just built cards that we bolted onto the disk drives and converted them ourselves. And after those started to be reasonably successful, the disk drive guys said, well, we can make that a lot less expensive. And from then on, right, it just took off.
Just one question for all of you before we ask for audience questions, which we'll do very shortly. But we obviously are dealing with an industry which has evolved a long way. I guess it's safe to assume it's still evolving, isn't it? So just let me ask each of you for your comments on, give me a percentage of how far along to full maturity we have evolved from the beginning of storage. How far along are we? Are we at 20%, 30%, 80% of the path of evolution for storage for computer systems? Mike?
50%. And the reason I say that is that I think one of Claude's charts is all of the innovation that's still left. You know, there's a complexity theory that says when things get so complex, the only way to eliminate the complexity is to stop doing it. And what's really happening with storage is it's getting so complex. And so what you love with storage and this whole idea of policy-based storage is you'd like to be able to go to just like a light switch and you turn it on and you don't really know where it comes from. The storage as a utility. We're you know, from that aspect, we may be at 20%, but from the functionality and the things that have to happen, we're probably about halfway there. And to me, that's the reason why I like Claude's chart about that controller. To me, it's a little bit ironic that you've got all these disk drive companies that make, you know, literally millions of disk drives a year. And
yeah,
really,
the number is up to about 300 million a year now on disk drives.
And the amount of money that they make on that, the net profit that all the disk drive manufacturers make is almost zero. And that the guys that are making the money are the people that they're selling to that don't make any disk drives, EMC, Network Appliance, and you know, the computer system manufacturers. And they're making 50, 60% gross margin when 80% of the cost of their subsystem, of the hardware cost, is in the disk drives. So clearly the value, as Claude said, is in the software and the intelligence. And so from that aspect, until we get to a more automated management that takes that complexity out, I think we're only halfway there.
Well, I think it's great that the subsystem manufacturers like yourself are making the money.
I like that idea.
So I'll give you a different number. I would say well less than 10%.
We're only 10% along on the path of storage evolution.
And the proof I would offer of that is that it doesn't, I mean, you can't spend 5 minutes thinking about this or even open the papers anymore and discover something that somebody within the storage systems industry would say, I can solve that problem. And I can solve that problem sooner than anybody else will. So just an example, within the last week, some guys at a well-known California bank were moving tapes from one facility to another, and they got to their destination and didn't have the tapes anymore. And the really unfortunate thing for those guys in this event was that the contents of that tape were the financial accounts of government employees, including a number of members of the Senate. So there will be hearings. I mean, this is something we have a job to do now. The phone is going to ring, and there's going to be opportunity to develop quick answers to this problem of sending around tapes in clear. So you can't but think about it for a minute and write down 25 things that you could go off and work hard on.
Okay, thank you. Larry Boucher, how far along in evolution have we gone?
Yeah, I'm definitely in Claude's camp, and I guess if you walk into any IT guy's office 10 years ago, they all have their infrastructure pasted on their wall. The center of their infrastructure 10 years ago was a set of computers. When you walk into it today, you see this round loop. Basically, we have gone, and it's, I grew up in a computer company, right? We were second sons forever. It is really nice now that the computer is becoming a peripheral. The fact is, the fact of the matter is, we started out as a compute-centric environment. We're just turning into a storage and a data-centric environment. It's just getting started. And we haven't even gotten to video on demand, and that's just a start. You heard some huge, petabyte-style numbers that we're each going to have. It's going to happen, and the heart of it's storage. So yeah, we're just barely getting off the ground.
So Randy, how far along in evolution are we?
I'd have to say we're closer to the 10% number than the 50% for all the reasons that have been given here. I think the storage components are commodities. You don't make a lot of money selling those things. The integration, the big megatrend I see is the movement towards network-centric, that everything plugs into the network. Computers plug into the network, storage plugs into the network, software runs on the network. So that fiber channel, that box that Claude showed is now something that plugs into a general network, a commodity network. All the boxes, all the network componentry are commodities. It's the software that lives on top that really makes it have value, where the money is to be made, and how to organize that is still a huge challenge.
Okay, we have a microphone in the central aisle for anyone who has a question. We'd like questions, please, not speeches of disagreement.
This is perhaps a philosophical question, but
Give your name, please.
My name is Mark Duncan. And why, we can draw these nice straight longs on, log axis by year, but why? Why hasn't it been faster, or why hasn't it been slower?
I think you're talking about the pace of
Areal
technology,
density.
areal density. We've had, I've sat in rooms where people have said, we've reached the limit of technology has been reached, and then somebody comes up with another idea, whether it's MR heads or super paramagnetic effect. And I think the reason for that is that the customer demand is what's driving that. Is storage capacity is doubling every year, so the vendors that are trying to solve the customer problem recognize that they need to be on that path, and so the competitive pressure drives the innovation to come up with that limit. I remember being at Control Data when the 3330 was being developed, and the 2314 was out as 28 megabytes, and the question that was being asked of the marketing guys was, who would ever want a 100 megabyte drive? Who could use all that? And it's the same kind of questions at Control Data when the first 6600 came out. We predicted 12. We would sell 12 supercomputers, and it would satisfy all the world's problems. So what happens is the demand for storage is insatiable, and the amount of storage that is now being born digital is something like 95%. And if you just take your digital cameras right now, if all of the pictures, if all of the film was digital, you'd have 80 petabytes of data per year. So people want to store that, retrieve it, and that's what's driving the technology.
Thank you, Mike. The gentleman standing over by the microphone now is Tom Coughlin, who probably has a loaded question.
I do. I think I have fun with this one. Can you make any comments about the people personalities and the personal passions in their effect on the development of this industry?
Personal passions. Well, I'll say a couple words. I don't know everybody in the storage industry, and I don't know everybody in the computer industry, but there has been a relatively small set of people within storage systems that have a combination of innovative capability where they can invent things, tenacity, and just plain will, to where they will go out and fight for ideas that, when you're looking at a particular set of function, you say, well, you know, why is this function being done in this box? It could be done other ways. And there have been certain personalities, and there's some of them in our company, and there's some of them in EMC and at STK and at Veritas that just cause things to happen on the basis of their brilliance and tenacity and eloquence and will. And I think the storage world as a whole has maybe a bit of a overabundance of riches of those guys. So I think we've done pretty well.
Next question.
Yeah,
Your name first, please.
Excuse me? Yeah, Brian Berg, Berg Software Design. I just want to say, first of all, thank you very much for what I've been hearing so far this evening. It was really, really good, really fun. Thanks. A couple of questions with regard to future directions. A couple of things, object-oriented storage and content addressable storage. Anybody have any thoughts on how those will enter into the scene over the coming years?
Well, it's obviously going to be extremely important. It's already been referred to. We're all going to put our photographs, the 80 petabytes per year of people's private photographs. How are you going to find it all again? So a lot of this turns into, whether it's object-oriented techniques, database techniques, or something, you're going to need very powerful software capability to find things, organize things, watch the things that you're interested in and present them preferentially to you. A lot of that technology has to be developed and integrated with the storage world to make that kind of personal storage management possible. And the cutting edge of that may be on the consumer side, maybe it'll be more on the enterprise side, but as that gets developed, I think you'll see it in all aspects of how people use storage.
Next question.
John Green. Claude mentioned that CIOs and CEOs learned in 1993 the value of spreading things. I might mention that a small bank in New Hampshire sent out an apology letter to all of their ATM customers. They only had 5 ATMs, that they had been down continuously for 10 days. However, they said, we tried to do it right. We contracted with EDS, the biggest independent supplier of these things. And they had 2 redundant data centers. The primary center in Colorado, it would automatically switch. However, when the snowstorm collapsed the roof and took out the primary, the switch didn't take place because the secondary was in the World Trade Center that had been blown up 2 days before. And even EDS, that can get their own people out of Iran, couldn't get that thing up in 10 days.
And the question is?
I'm sorry.
So,
it was an anecdote.
Not everything is perfect, obviously, but it's one sort of interesting phenomenon about history that the 93 event gave us 8 precious years to go get this right. And when the event happened in 9/11, with the exception of some certain cases, I mean, this is obviously one of them, but the vast majority of people that had IT equipment in that building did not lose their data. And in fact, most of the businesses that failed to recover because of loss of people and not loss of data.
Yes, earlier in one of the presentations it was mentioned that EMC had pioneered what popularly were called the remote site mirrors. And several of those companies in the World Trade Centers did have those remote site mirrors in New Jersey and other places, and were able to have computers up the next day, actually.
And I think another study that came out of the 93 was that it wasn't just it was the fact that they couldn't get back in the building for 30 days. And what caused them to say, if you couldn't, and as the study came out and said 3/4 of the companies that did not have a disaster recovery plan went out of business because they couldn't run their business for 30 days because they couldn't get back in the building. And so that's really what was as important as anything else.
Next question.
Hi, my name's Jeff Thompson. I sort of intimated from what you said about being at the 10% and the future and network storage and a couple of other things, that you sort of see the future as storage being a utility that you have a pipe to and a switch to. Somebody mentioned a switch. And I'm a network guy. I'm just wondering how big you think each person's pipe is going to be. We know how big the pipe is for water into a residence. What do you think it will take to service your great constituency once you get this hot throbbing center of storage?
Well, Bernard Daines, who gave us both 100 megabit and gigabit, his latest decision, his latest job is to give us gigabit to the house. In other words, he really believes he's going to be able to do gigabit over twisted pair last mile. If he can do that, I think that's going to last us for a little while.
Got time for a couple more questions? Go ahead.
Okay. I'm Steve Bargova. Two quick questions. The first one is, what's the potential for microdrives to compete with semiconductor flash NAND type devices? And then the second one is, since so much of the money is being made by the subsystem vendors, why don't the disk drive vendors wise up to that and do it themselves?
Or sell the disk drive business to somebody else,
for example.
And the first question, it's really interesting, but I can remember when CCDs were going to replace disk drives, and then bubbles, bubbles were going to replace disk drives. And, these were both things that we were seriously looking at IBM in terms of, oh, God, is this going to really, replace disk drives? San Jose, at least, was, really still interested in round brown. But somehow it just doesn't happen.
Actually, I think I'm asking the opposite question, which is that NAND flash devices are used in lots of digital cameras and so on, and people are talking about using microdrives in those.
Oh, well, as long as the memory requirements are low enough, there's good arguments for not using a disk drive, right? I mean, if you can get by with something that doesn't store that much, then there are a lot of technologies that are better than a disk drive. The disk drive is a phenomenal technology for storing very large amounts of data very inexpensively and being able to get at it quickly.
And I'd like to defend my 50%. I think that we're talking two different things. I think that because the disk drive guys don't make any money, because all the money's in the software and the upper layers, that's why you see companies like IBM selling off the disk drive division to Hitachi and people getting out of that business. There's no money to be made in making these spindles and the technology. Where the money is to be made is in the intelligence that goes with it. So I don't think you're going to see a lot of storage innovation in the hardware. I would say that it's all going to be application-based storage. And I think to your question, I think this is where the future is going to be. Is all going to be a network device. You're not going to see a lot of these super storage centers. You just think of all the things that are going to be networked, billions of devices. Your dog is going to have a collar and things that you're going to be able to track in a global position. It's already being embedded in animals and everything else. How do you talk to all this stuff? And I think what's going to happen is we're going to think differently about storage. It's all going to be application-based. And that's where the innovation is going to be, is going to be talking to billions of devices in a network fashion as opposed to innovating on brown round storage.
Next question.
Okay. My original question was about...
What's your name, please, again?
I'll tell you later.
Oh.
My original question was going to be about solid-state storage. I'd like to ask two different questions. First, what do you think the impact of Internet Protocol v6, as opposed to current v4, will be on network storage? And second, talk a bit more about the need or the opportunity for security in storage.
Well, I think V6 is going to happen. I don't think it's going to have a huge impact. We've already solved the problem here. China is driving V6. But because of that, it is going to happen. At the point in time that we want a different address on every single grain that we drop everywhere, maybe V6 really does become important. But I mean, regardless, it's not a lot of overhead, so it's not. I don't think it's a major issue. As far as the second question,
Security.
Well,
I'll talk to security maybe. I actually think that's going to be a huge piece of the debate in the coming years, and it's going to be driven much more by people whose job is social policy as opposed by technologists. So there are a number of gadgets that we can go off and deploy and things that we can do, but I think there's a very lively debate that's going to happen around how data gets created, who's allowed to see it, what kind of accesses are going to be allowed, and there will be a fairly hefty government compliance arm to qualify devices for use in certain applications and to examine how those things are being done to prevent accidents that banks could commit, or insurance companies, or health companies, or anything like that.
Let me just point out there's a big issue now in the consumer
Do you have a question?
Yeah, okay, question.
Please ask a question.
Sure, okay.
It's like Jeopardy.
Digital rights management, what impact do you think that will have on security? I mean, beg your pardon, storage.
Well, again, I mean, that's a social and business question. I mean, we saw what happened to Napster, right? I mean, Napster proved that everybody would download gobs and gobs of music as long as it was free, and so they were in the business of giving away other people's IP. And we saw that put to a stop. So technology is needed, and people that own intellectual property will insist that they get paid somehow for all this free exchange that everybody wants.
And I think security, digital rights managers, just in a paper today, I think, as Microsoft is in another lawsuit with digital rights management issues, I think that whole area is the area that you're going to see the biggest and fastest growth and innovation is security and storage and networks, and that's where a lot of the innovation is yet to come.
Next to the last question.
Yeah, Jim, my name's Robin Harris. And I'm really torn between asking a question about the future and asking a question about the past. If we're the future, it'd be the future of God boxes. You know, VCs dropped $1 billion on them in the last 5 years. But I want to ask a history question. I was in the StorageWorks group in the 90s. I was watching EMC pummel IBM, which, you know, owned the rotating Rust market at the beginning of the 90s, and I was watching EMC pummel IBM year after year after year. What was going on inside IBM with all of their, you know, all these patents that they told Randy about, you know, just all the research and this incredible technological skill and this market dominance? How did they ever let EMC become a dominant player in the RAID market?
Good question. Well, without...
Does Claude want to answer that one?
So it wasn't a real pleasant experience. But fundamentally what happened was we were too successful and too invested in the older model, and by older model I mean the 3990 and 3390 native CKD style devices, to where it was extraordinarily difficult in the mainframe space, which is where the problem happened, to import the innovative designs of, you know, RAID and SCSI and the technologies that were the right ones. Now, we did that okay in areas where we hadn't been invested in the past, so we had a really nice product that came out on the AS400, the 9337, made a lot of money on it. We did SSA, made a lot of money on that, on RS6000. But the real damage was done on the mainframe, and it was because we were too stuck in the native CKD, you know, that form factor of design.
And I maybe make a comment there. And I spent the last 30 years competing against IBM, and it's uncomfortable to try to defend IBM. But I think an interesting book that I found fascinating for any history buff is Clay Christensen's Innovator's Dilemma, and takes the whole disk drive industry. And what it basically shows is that very well-managed companies, whether it was IBM or Seagate or anybody else, Micropolis, a lot of these companies that had leadership positions, Connor Peripherals, failed because they were a captive of their customer base and of their success, and something else came along at the low end, new form factor, and basically took over. And that's really, I think, an interesting lesson.
And our last question.
John Massey. It's great to have a panel like this with this depth of experience. I always like to ask such a panel about surprises. So could you talk about surprises in this long history, like things you expected to happen that didn't, or things you didn't expect to happen that snuck up on you, or things you thought were going to happen soon but took a lot longer? Just pick these. What in your long histories did you find to be surprises?
For me, I left IBM because they weren't going to get into the microcomputer business. I mean, they literally were not going to get into it. And so for me, the PC was an amazing surprise. I mean, it was a stochastic shock to the industry in any case. So I think it was a surprise of sorts to everyone. There were microcomputers out for long before the PC, but the PC defined the industry, and it allowed it to really roll. And I was amazed.
For me, I would say that based on kind of coming at it from a university side, that I would have thought that the first companies to capitalize on the ideas of RAID would be a company like IBM, major dominant player in the storage industry. And the value of these university projects where you just talk about what you're doing broadly, you never know what small company will come along and jump on an idea and reach market dominance because they're more nimble and faster to do it. It's not just the EMCs, but for example, Compaq, one of their first controllers for a new backplane interface, they read our paper and decided the first controller they would build was a RAID controller. So, you never know how these ideas are going to get out there into real products. And while we work closely with companies like IBM, we followed a strategy of not being closed to just report our results to those companies. We talked about it broadly, and that helps the industry in general go. And once the competitive pressure is there, it leads to the innovator's dilemma being broken inside a company, that the competitive pressures force an IBM to adopt those new technologies and move forward.
And I would comment that if anybody really wants to follow that, they ought to go back to Mike's suggestion and read Clay Christensen's book, The Innovator's Dilemma, which came out in '97 and was one of the biggest business bestsellers at the time. More than half of the case examples he used were disk drive industry examples. So there's a lot there. One last question.
I'm a bit confused about the claim that you have, 30% of work to do in the area of security, and at the same time, everything is going to be network attached. That once I put my bits on the network, anybody can read them, in my opinion. And so security is my job at the other end. I don't send anything to you guys that's not encrypted. So what's your security job?
I guess we should comment that they're concerned with making storage more efficient. It's usually somebody else's job to figure out how to protect the data, isn't it?
You will see encrypted files. You will see people embedding into storage systems, encryption, digital rights management. All those things, I think, are going to happen. I think that's the new frontier for storage, and so I think that will be a natural result of the concern that he has. And
well, I'd like to thank each of our speakers. Isn't it obvious they know what they're talking about?
And that's why we've had such a terrific panel tonight, as well as a terrific industry. And the depth and breadth we really appreciate. On behalf of the Computer History Museum, thank you again, panelists, and thank you, Jim, for organizing this. It was really spectacular.